स्पीकर
ये है मतलब किसी से ये होता है
Sajan Singh? No. ठीक. Shall we start? Yeah. Okay, so that is how this. So whatever the problem, see there are some distinct advantage when you use the gravity analysis. As I told you that the relative standard deviation of less than 1%, and we does not need any kind of a reference material. And what are the disadvantage? Disadvantage is that you cannot do when the materials are present in the ppm levels or less than 1%. Then it's difficult to perform a gravity analysis. So that's how we started this volumetric analysis. See, volumetric analysis is basically involve the acid-base titrations, redox titrations, and then the issues which is comes in this case of a in case of volumetric analysis that been again surpassed by using the colorimetric analysis. In the colorimetric analysis, the analysis is done by just developing a color and a very small amount of that analysis is possible in the ppm level also. So that's how this journey from the gravimetric to the colorimetric and then to spectrophotometric. Then we discussed the importance of sampling. See, sampling is a very, very crucial part of the any kind of analysis. Because if you had committed any mistakes in drawing samples, for example, your sample is not representative one or not homogeneous ones, then there is no, whatever the benefit you are having a good sophisticated laboratories or sophisticated equipment, there is no use because actually you have done a mistake at the grassroots level itself. So that's how you are not, that's a very important part that one must take the representative as well as homogeneous samples. So one has to make sure that whatever the sample has been withdrawn from the bulk, it represents and I say homogeneous throughout the and represent that bulk, the concentration in the bulk sample also. See, once you withdraw the samples, see most of the time it's not possible to do the analysis immediately. But generally we bring the sample from the site to the or from the one lab to the if you are involved in the synthetic chemistry, you bring you do the synthesis in your lab and then give the sample for the analysis to other labs. So there is a time gap. So the time left between the storage, between the sample generations to the sample analysis, there is a chances that you will lose the your analyte of interest. So one has to take care, and we have discussed the many cases in which the analyte will be either get absorbed on the container, absorb or adsorb on the container, or it may be something of similar kind of an analyte will come from the walls of the container also. And in case of gases also, if we are not taken proper precautions, then it will react with the atmospheric gases actually. Like that we have seen the case of the sulfur dioxide actually. Then we discuss about the sample digestion. The sample digestion is again a very crucial step actually. See, from the bulk of the matrix, you have to take a very, very small amount of your analytic. And then one has to make sure that the whole analyte you should come out of your matrix. That we have seen, for example, if you are having some lead content in any soil matrix, so you have to break. You know that they say basically soil is nothing but the aluminum silicate matrix there, and then you have to bring out that aluminum completely out of this thing, so breaking that aluminum silicate matrix, and which is only possible when we do a very strong acid treatment and help of HF actually. Hydrochloric acid has to be used to destroy the silica or to break the matrix of the silicas. Then in this basically when we are looking for a very, very small quantity in a ppm or ppb or a ppt level of these things. So that is the issue when that will be termed as a intricacy with the environmental analytical chemistry, or when we are doing the very ultra trace level of chemistry. So there, one has to be more precaution has to be taken, to be given, so that the your element of interest will be come out totally from those things, and you will be able to do the analysis properly. So what are the precautions are there has to be done that we are discussing, already discussed. Then we had discussed about the separation chemistry. The separation chemistry, we had discussed about these, solvent extractions, ion exchange, and then the chromatography. See, in case of solvent extraction, I have given the example of that you are using you want to separate, you want to do the analysis of the iron and aluminum, the uranium matrix. So it is not possible. See, suppose I am using for this thing ICP, yes, because my uranium is about say 99.9%. And then if I use I will dissolve the sample as such, so most of the interference will come to the uranium, and I will not be able to analyze the iron and aluminum in that. So for that, what we take the help of the solvent extraction, in which uranium will be selectively taken out in the tributyl phosphate, and the iron and aluminum will be then remain in the aqueous mode phase, and then we can do the analysis properly. And in case of ion exchange chromatography, also we have seen the various this anion and cation exchanges are there. So depending on the whether you want to separate the anions or cations, so you can use the various kind of the ion exchanges. And chromatography. See, basically in the case of chromatography, we have seen that both kind of a chromatography, they are basically either differentiate based on their mobile phase and a stationary phase, and then the various kind of interaction between the various attractive forces. Attractive forces means ion exchange or these size exclusion chromatography and others which we have discussed which we had already discussed when we discussed about this chromatography techniques are there. So in this we had seen both gas chromatography and the high pressure liquid chromatography things are there, and of course we had talked about something about the paper chromatography also, where we had seen that how the retention factor will be evaluated. After finishing this chromatography, we come about this atomic spectrometry. Atomic spectrometry is nothing but we have studied the interaction of the electromagnetic radiation with matters. So in this, before going to the atomic spectroscopy, we discussed about the molecular also, that about the UV visible spectroscopy. So where the molecular transitions are, are there for doing the determination of the various analytes. And we have seen that this absorption chromatography is based on this principle of a Lambert-Beer law. And then in this case, we have seen that what are the what are the constraints when we doing the analysis of absorption spectroscopy, because of the non-linearity at a higher concentrations. And then comes about this atomic spectroscopy. See, in atomic spectroscopy, we have seen both this flame atomic absorption spectroscopy, that is FAS, and the graphite furnace atomic absorption spectroscopy. So these are the two various cells. In case of flame, we have a flame as a atom cells, whereas in the graphite furnace, graphite as a furnace as a atom cell. Whereas there are certain elements like arsenic, selenium, which are the which gives their best detection limit when they have hydrate. So in this case, we use the quartz cells where we convert the arsenic and the selenium into the hydrate formation by using the sodium borohydrate and HCl mixtures. And then we do the analysis where in all these cases, this most important thing, we have to bring the bring that molecule in the atomic form, and from the atomic forms at a particular whatever this, whether we are using this hollow cathode lamp, HCl hollow cathode lamp, or we are using the xenon arc lamp where we have a continuous spectrum and with the alpha monochromator. So at that particular wavelength, they will be absorb the light, and then we go from the ground state to the excited state, and we measure that decreasing the intensity of that particular wavelength. That's how we do the determinations. So most important thing in both of FES and GFS atom generation, that the atom protections. And in this case, we have seen the various kind of interferences, whether it's a spectral interference. Whenever spectral interference are there, then we try to choose the another lines actually, because there are some many lines are there. So if two lines are very close, so we can choose the third line. There we have a minimum interference. That's how we avoid the spectral interference. Then there are certain ionization interference, because there are certain element which gives like alkali metals and all those things, they give lot of electrons very easily in the flame. So we have seen this how to we use the ionization suppressor, like that we use the potassium chloride solution both in the standard as well as the in our samples, this one. So that's how we avoid this ionization interferences. And then there are certain background interference like the continuous molecular interference are there that we are that we are avoided by using the this deuterium lamp. Okay, that, and then we have seen then we have also seen that certain interferences can be corrected by using the Chebyshev correction, in which we applied the magnetic field around the atoms, and that's how we avoid we can carry out this background correction. And the Smith-Heffay, generally we avoid it. Of course, that also has been inbuilt in this thing, because the measurement has to be done at two different current. At a higher current, there is a possibility that we are damaging the filament if we are using the hollow cathode lamp. So that's why it has been generally avoided. Then we had come to the emission spectroscopy. In emission spectroscopy, we have seen that see here both we convert our molecules into atoms, and not only atoms, even ions are also suitable actually in case of ICP OES. So whether it's atoms or ions, so we can change either the atomic emissions lines or the ions emissions lines. So whatever the best suited, we can take the help of this. We can take in the case of ICP OES, and generally the detection, see in case of FAS and GFS, what are the constant is that we can go only up to the temperature of the 3300 degrees centigrade, that if we are using the nitrous oxide and as clean flame. So at that temperature, there is many, for example, rare earths and there are some other compounds are there. It's not possible to break them. So that's why we need a plasma. That is we got it in case of ICP OES, where we have an analytical zone about say 5,500 to 6,000 Kelvin. So where generation of the atoms are there, and they will convert either into the both, you can convert your molecules into atoms and then to ions. And of course, you must be remember, in case of it, because even if a solid sample is there, you have to bring them into the solution, and then how these first step will be there. You bring your solution, and then desolvation. First is nebulization, desolvations, then atomization to bring this thing. Then some of these things we had discussed these, this mass spectrometry. See, mass spectrometry, while discussing the mass spectrometry, the most important step is that, again, because this based on the M by E ratio. So first step is the ionizations, and once the ionization has been done, so it has to be fed into this mass analyzer. So we have seen the various kind of mass analyzers, and then we have also seen the various kind of detectors. So we have seen in this case three things: the various ionization sources, then various kind of mass analyzers, and then various kind of detectors when we discuss about this mass spectrometry. In our last lecture, we have seen this some basics of the electrochemistry. See, while discussing the basics of the electrochemistry, basically electrochemistry is nothing but, there's two types. Where we have converted the chemical energy into electrical energy, which is in the galvanic or Daniel cells, and electrolytic cell, where we are converting the electrical energy into a chemical energy. So, reactions. So that's what we do, all kind of plating and all those things. And then we have seen how to write in how to write in electrochemical reactions actually. So cell reactions. And then basically there are three, when we are discussing, when we are doing any kind of a analysis, means we are determining the any kind of concentration of any analyte. So basically we are doing either a polography or a voltammetry. So these are the two things which we had discussed while discussing this thing. And before discussing those polography, we discussed about these Nernst equations. The Nernst equation is nothing but the giving a cell reaction. The redox potential of this relate the redox potential of the cell reaction with the standard redox potentials, and then Ilkovic equation which relate the diffusion current, and we have seen also what is diffusion current, how to relate the diffusion current with the concentrations, and then the importance of the characteristic halfway potentials. And then what is the most important thing in case of while doing the analysis of this electrochemical analysis is that this the characteristic halfway potential is not only, it's not possible only to determine the element, but its chemical form also, because these electro-wave potentials are different from the atom as well as the chemical species. So that's how various chemical form also of the element of the speciation is possible by using the electrochemical analysis. And depending on these various kind of electrode, see, we had seen that how to improve from the classical polography. So there are certain problems are there in the classical polography, because we cannot control the size of the mercury drop as well as the apply the voltage. And then the is not possible earlier in earlier polography before the an improvement in the microprocessor of this electrical instrumentations. We cannot distinguish between the 0.2 volts actually. But when we had improved the microprocessing, we can have a resolution about the more than 0.02 volts. That's how we can determine the concentration in the ppm or the ppb range. And here we have seen the determination of the uranium by using the adsorptive streaming voltammetry, in which we have done the pre-concentration of the uranium uranium by using the chloranic acid. Similarly, we have seen the determination of the anthracene, glassy carbon electrode. So how important? So that's how we have shown the importance of the electrochemical analysis. And after discussing this electrochemical analysis, we discussed about these basics of the thermal chemistry. In this, as I told you, thermal chemistry is nothing but when we are studying any reaction with the help of variation in the reaction with either in the temperature and the time. And in this, if we are recording any kind of a mass change with temperature, it will terms as a thermogravity, that is TGA, and sometimes we take the derivative of the mass, then it's termed as a derivative of this the mass, we can take it. And then we discuss about this DTA and DSC. See, DTA and DSC, in both the cases, we along with the sample, we use the reference material. So in case of a DTA, we observe the variation in we observe the variation in the temperature difference between the reference and the sample. Whereas in case of the DSC, we measure the heat flow. Basically, we have to keep both the both this reference and the sample at the same temperature. So for that, see if any reaction is going on with this exothermic or endothermic, depending on we have to either to flow we have to give the more heat to the system. So or taken out from the heat from the system. So that's how we recording various DSCs and some of the application of both DT and DSC also we have discussed and what are the characteristics of the reference material in case of DSC and DTA. And after discussing these things, we comes to the thermometric titration. The thermometric titrations, basically, they are titrations as we discussed in acid-base titration, redox titration. But in case of thermometric titration, there is a large change in the enthalpy, and that has been recorded because at the end point, there is a release of energies are there. So that has been recorded. So that will be termed as a thermometric titration. I think we had discussed 3 examples, HCl, NOH, and then we had this calcium and magnesium determination by EDTA and determination of boric acid concentration by using the sodium hydroxide. So this is how we had done so far. We had, almost cover about the 70% of the course given to me during all this advanced material characterization course. Now today what we are discussing basically the technique which we had already learned it. So that's when we combine these two techniques, that is a combination of technique and their applications. See this, as I told you, the technique itself is a versatile one, but when we combine these two techniques, it becomes more versatile. But then they become more sophisticated and their day-to-day care is also becoming a very, tricky. And so let's come. See various analytical instrumentations, whatever the, various part of the analytical instrumentations are there. So here, sample is there. That sample either has to be, interact with the light, heat, current, and a voltage. And because of this interaction between these either heat, light, and a current voltage, there are some changes in the sample is going on. Okay, those sample has been put into a detectors, and then from the detector, whatever signal is there, it will be coming. It will be fed to a processor, and then to a recorder where we do it. See, all these instrumentation, whatever we had discussed so far, and whatever even other instrumentation, they are based on those things only. See, there is the sample, and then sample has to either interact with any of these, either light, heat, or current, or voltage. Changes are there. Then because of those interaction between these stimulus and the sample, there will be some changes in the samples. And those, because of those changes, there is some signals are producing. Those things will be fed to a detectors, depending again upon the what kind of signal we are getting it. And then that signal has been fed to a signal processor and then the recorder. So hyphenation technique, basically a combination or coupling of two different analytical techniques with the help of a proper interface. Hirschfeld 1980, he is the first person who introduced the term hyphenations, and that referred to the online combination of a separation technique and then one or more of spectroscopic detection technique. See, as we've seen, the chromatography produce pure or nearly pure fractions of a chemical component in a mixture, and the spectroscopy produce selective information for identifications using standards or laboratory spectra. You can use both standard as well as the libraries are available. So you can take the help of those library spectra also. The hyphenated technique is developed from the coupling of a separation technique and an online spectroscopic detection technology. The number of existing techniques has been combined to expand the utility, and the direct conjugations of a chromatography technique with a spectroscopic examination of a separated fraction constitutes several powerful analytical technique. And generally, whenever we are discussing about this hyphenated technique, either there will be a slash or a hyphen. Actually, this, for example, here it is shown that HPLC, electron spray ionization, mass spectrometry. So if there is HPLC and ESI, there is a slash is there, but it can be hyphen also. That's how we do the we denote various kind of a hyphenated techniques. So the hyphenation does not always have to be between the two techniques. The coupling of a separation or a detection technique. And recently, more than two techniques coupled together to form a more powerful integral system and have revolutionized the trace element analysis industry. It's really actually it's really revolutionized basically all this analytical concept and the our ability to determine the chemical species. See, as we are progressing, see, for example, I give you some of the very simple example, and that we'll see in the last of the lecture also. See, arsenic 3 and 5, chromium plus 6 and plus 3. See, their toxicity are varied. Similarly, if there are many, so many arsenic sugars are there, that means compound of arsenics are there. So their toxicities are varied. So nowadays, people are not interested in knowing what is the concentration of the arsenic or a chromium. They want to know what species, in what form they are presented. So these hyphenations actually will revolutionize those kind of analysis, and it's really helpful and give us a meaningful results, so that their toxicity can be determined in a very pinpoint manner. So that's how we say that they are revolutionized the trace element analysis industry. And also they also termed as a double hybrid. For example, this is a liquid chromatography photodiode array, NMS. This is LC, PD, and MS. LC, MS, MS. Basically, here the liquid chromatography is having a combination of two mass spectrometers. And then this LC and MS instrument have become available and have been applied to various kind of pharmaceutical problems. Actually, they are having a much utility. These hyphenated techniques having a very important tools in case of a clinical study of the various drugs. And the online coupling of this solid phase extraction. See, before injecting your sample itself, you are doing the pre-concentration. So the solid phase extraction, solid phase micro extraction, or large volume injection can be incorporated. That is this here, instead of before feeding your samples to the LCMS, it has to be either you can have this solid phase extractions, or you have a solid phase micro extractions, or large volume injections. Those equipments can be coupled with the LCMS. So as we already discussed, this basically hyphenations techniques their separation can be hyphenated, separation identification can be hyphenated, identification. For example, two MS had been coupled together to give a various useful information about the compounds. So this is generally a block diagram how this this hyphenation of the various technique is possible. So here, before feeding your sample to the either GC or HPLCs, or the C means capillary electrophoresis, it can be done by using the solid phase extraction or a large volume injections. So those things, for doing the pre-concentrations. After doing the pre-concentration, you can put in the separation technique, and after doing this separation technique, they can be put into a detection techniques. Detection technique can be PDA, infrared mass spectrometer, NMS, or a thermal lens spectrophotometric. And then, optional multiple application, that is the further detection technique can be it can be further hyphenated actually, as we have seen in case of a MSMS. So there are the various advantages which are associated with this hyphenation technique. They are fast and accurate. High degree of automations are possible. Then the throughput samples are, very high than compared to the individual one. And the reproducibility also is multifold better than compared to the single ones. Then reduction of contamination due to its closed system, because you are not bringing your samples. See, first you are doing the separations. After doing the separation, you will take the detections from one instrument to the other instrument. So those things also we avoided. So that's how we bring about the reduction of contamination, and then separation and quantification achieved at the same time. So these are the list of various hyphenated technique, that is inductively coupled plasma mass spectrometry, gas chromatography mass spectrometry, liquid chromatography and mass spectrometry, liquid chromatography with the nuclear magnetic resonance, and then this is EC with MS, that is electrochemistry mass spectrometry, capillary electrophoresis mass spectrometry, gas chromatography IR, then LC, liquid chromatography with coupled with the MSMS, then liquid chromatography electron spray ionization, and MALDI. MALDI is nothing but the metric assisted laser disruptions or ionizations, and this is with the time of flight. Then US, GCMSMS, GCNMR, and then GCAES and ICP-OES. That's already we had discussed both of this ICP-OES in detail. Now, before going to the further part of these lectures, I will discuss this ICP-MS, because as I told you when we discussed about this atomic spectrometry, and we had discussed about a very small part of the MS only. Now today we discuss about this ICP-MS before giving a brief details of the others hyphenated technique. And as usual, if I do not know how many people of you are listening right now, if you have any queries up to now, please put your question in the chat box, and I am very happy to share whatever experience I am having with you. Any queries? Yes, I do not know who had asked this question. Yes, you can do the analysis of uranium. Actually, so far I have not done it. But if you are having a uranium hollow cathode lamp, but I have not seen also uranium hollow cathode lamp. See, in AS, it's very important that you should have a hollow cathode lamp, and we are not used. So of course we are having a this xenon arc lamp, that is continuous source flame atomic absorption spectrum FA AS, but we are not done it. But we most of the analysis of uranium we done by using the ICP-OES. But as I told you, if you are having a uranium hollow cathode lamp, one can do it. But as such, we are not practicing so far the analysis of the uranium by using the AAS. Of course, we are doing it on a regular basis, determination of the uranium by using the ICP-OES. We use the ICP-MS also. We are using the laser fluorimeters, and as well as the this voltammetry also. That's what we had discussed also, that adsorptive stripping voltammetry, where we pre-concentrate it on a chloroanilic acid on a mercury drop, and thereafter we can do the determinations. But so far we have not done by using the AS actually, man. But there is no idea, because I don't remember exactly the line also. If I remember the line, I can tell you we can done the analysis by AS or not. Eh? Yes, see, it is definitely possible to give the detection limit. See, otherwise, why this manual has been there? But again, you have to use the, the condition which has been defined. So definitely one can achieve, and we are achieving it also. See, for example, detection limit of the various detection limit. Actually, in the manual, whenever any manual is there, I don't know which for example, ICP-US. See, in ICP-US, the various detection limit has been given for the various elements which are possible by doing the analysis by using the ICP-US. Then one can use those ideal conditions. Ideal condition means the condition prescribed in that particular protocols, and definitely one can meet that detection limit. Anurag, somebody was told that you are not audible, sir. Can you- पहले बोला, I think अभी नहीं है, पहले था ही, होटल पहले. Okay. Okay. So if there is no more question now, let's move to the, move further. That ICP-MS instrument, the ICP-EMS instrument consists of, these are the parts, the sample introduction. As in all cases, the first is sample introduction. Then again that ionization, how we have to bring the ionization, that we use this electrically coupled plasma torch, and then plasma vacuum interface. See, one more important thing is that I do not know whether, if you have a feeling about this equipment, then only you can understand. See, all this system, they are working on the atmospheric pressure. But once you have to feed your ions into the basically mass analyzer, so you have to put in a vacuum actually, and not only vacuum, that is vacuum up to 10 to not only 10 to minus 3 to 10 to minus 6 torque. So that's a very crucial part in case of a ICP-MS, that how to bring doing from the atmospheric pressure to the 10 to minus 6 torque, such a low pressures. So this is called a interface, that is called a plasma vacuum interface. Then ion optics, we'll see that what is the importance of the ion optics, then the mass separation devices, and then finally as the ion detectors. So the sample introduction system is basically consists of a three-part, that is a pericyclic pump, that is a very small liquid has to be drawn at a time. Then that liquid has to be, with the help of nebulizer, it will aerosolize, and those aerosols put in fed into a spray chamber. In this spray chamber, the whatever the large droplets are there, suppose any large droplet been developed, they will be drained out, and then other small droplet will be fed into the plasma. So there is another way of doing this, basically atomizations, to bring the atoms into the plasma. How we can do it? That we can use by the laser ablation. See, in case of the solid samples, we can use these laser ablations and introduce the atoms into the plasma. That because of the laser, you can evaporate your samples into the vapor form, and those can be fed into the plasma where it will be get ionized itself. So laser ablation is a powerful sampling technique, and in this solid sample can be analyzed directly, and application include the geochemical samples, coating, and the solid state technologies. And what are the advantages of this thing? The LOD are in the order of microgram per grams, and they have a very good spatial resolutions. So what is happening in this? A powerful laser is focused to the sample in an argon, that is inert atmosphere, and a tiny portion of the solid is vaporized, and the resulting samples containing aerosol. See what we have done in the case of a liquid, we have used the nebulizer. but here we can use these laser ablations. So those aerosols will be swept into the plasma, and where it is atomized and ionized, and these ions will be further, fed into the mass spectrometers. So, with this, this small crater has been formed with when we are using these laser ablations. Okay, and see, there are certain issues are there which of the laser ablations. So, due to ablation process, it is said to be dependent on the wavelength and pulse duration. So, if we are using the femtosecond lasers, actually, I mean, those effects can be overcome, or even we can use the shorter wavelengths of this lasers. The technique, though definitely it looks like destructive, but can be described as a minimally invasive because of the small size. Because this is the crater which has been formed because of the laser on the solid sample is of a few microns or maybe maximum of the 100 microns. So this is in case of a liquid sample where we can use both cross flow nebulizer as well as the concentrating nebulizer. This is a diagram for the concentrating design, and this is for the cross flow. The cross flow, can be used. Generally, we use these concentrating nebulizers, but whenever the TDS is about say 0.5% or somewhat, nearby 5.5%. Otherwise, we have a TDS of less than 0.5% actually in this case. So whenever the TDS is high, then in that case we use this cross flow design nebulizer. And see, whenever there is some organic solvents are there, because whenever we introduce the aerosols or the organic solvent into the plasma, there is a very high generations of the electrons are there because they immediately get volatilized, and because of that there is a basically it's an electronic engineer's terminology. There is because of the large generation of the electron, there is some mismatching in these frequencies are there, and because of that, plasma will be get shut down immediately. So generally, in this source of organic solvent, one can use this ultrasonic nebulizations, and what is the advantage? Terms of what is the advantage of this? What are the characteristics of these ultrasonic nebulizers? It uses a ultrasonic generator, and that to drive a piezoelectric crystals at a frequency ranging from 200 kilohertz to 10 megahertz. And this pressure disrupt all this thing has been shown here. The pressure disrupt the liquid air interface, and resulting aerosols is swept. These are the resulting aerosols will swept into ICP torch by a stream of inert gas. That inert gas is here again we can use the argon, where it is ionized and subsequently fed to the mass spectrum. That is the mass analyzers. So that's how we can use these ultrasonic nebulizations. So we have seen here three different ways of introducing the atoms into the plasma. One is the simple, either we can use these concentrating nebulizers, and then we have seen in case of high TDS samples, we can use these cross flow nebulizers. Then if we are having this laser ablation, see laser ablations is a very sophisticated, LAICP-MS is a very sophisticated one. So if you are having a laser ablations available with the hyphenated with ICP, we can use the introductions of the atom into the plasma by the help of a laser, in which the solid sample will directly put into this plasma. Then we can use this ultrasonic nebulization in case we are having these these solutions which having a high organic content. So I think there is some Yes. See, I don't know who had asked this question. Sajjan Singh. See, as far as our, because recently itself we had conducted one of this intercompany exercise between our group itself. So our detection limit, although we are having a resolution of about say 9 picometers in case of our ICPOS, but our detection limit, about the 400 pp, not even 1.4 ppb. But definitely, if you are having I do not know which instrument you are talking in actually, man. See, there is a many kind of a different kind of ICPOS are available. Whether it's which make you are talking, whether it's analytical or horrible or which one. But definitely, if you meet those, the ideal condition which is given into the manual, you will definitely go because those detection limit as given on the manual is a very rugged one because the company in general do a lot of R&D before putting those values there. But they may be, you have to see the what ideal condition they are defined it actually. Understand? So it's possible that you can met those conditions. But as I told you, my practical experience, I have not remember what exactly in case because we are having Activa ICP-OS, what detection limit is given in the manual. And in our case, we see when we are doing some R&D works, for example, I have many paper published for the detection of uranium in the groundwaters. See, in the one of the work, we had gone up the detection limits of the 20 ppb by ICPOS. But in general, when we look for the sample, because when we are looking for the samples, you don't do that kind of ideal situations are there. So in these ideal situations, our detection limits are 400 ppb because we want that RSD should not be more than 5. Okay. See, whenever we are doing any kind of analysis by using the ICPOS, we generally restrict ourselves to 5% RSD. Understand? I do see in this 1.4 pp, what is the RSD, instrumental RSD? That also has to be seen. Uh, Anurag, Anurag, there is some, I think, issues are there because you are not audible, sir. Uh, is it okay now? Is it okay now? Sajjan Singh is okay now? Audible, na? It is 410. 410. Okay, okay, okay. He say afterward also. Okay. Yes, yes. Okay. So this how I think we have discussed this how the plasma get generated when we discuss about this ICPO as also. So same thing here also. An electric spark is applied to introduce a free electron into the gas stream. Here again, these are three concentrated rings are there. Electric spark is applied to introduce free electron into the gas stream, and which are then accelerated by rapidly changing that electromagnetic field that is at the frequency of the 27.12 megahertz. Generally, there's a two type of a radio frequency has been given. Either one is the 27, other is about the 47 megahertz. So all are both are okay. So one cannot say that. But some people, some of the companies say that my plasma is more stable because I am working on the 47, some say that 27. But actually, there is not much issues are there. So either you can use both 27 as well as the 47 one. And then these electrons collide with the argon atoms, forcing the loss of electron, which in turn accelerate in the oscillating electromagnetic field. and resulting in a multiple temperature zone within this produced plasma. So you can see that here we have a plasma zones from the 10,000 Kelvin to 8,000, 6,000. So this is our analytical zone where we do where is the most preferred one. So this is the ion formations. The sample undergo a number of physical changes that start at the preheating zone and then continue through the radiation zone before it eventually a positively charged ions in the analytical zones. And mostly singly charged positive ions are generated because all this has been well studied. So more than 90% of the positively single positively charged efficiency is about more than 90%. So this is the interface where we, bringing from the atmospheric space to the vacuum one. So this interface basically is just, that interface transport the ions efficiently and consistently from the plasma source, which is at the atmospheric pressure, to the mass spectrometer that is about the 10 to minus 6 top. So this interface, what is that interface? The interface consists of the two metallic cones. One is the orifice of about 1 millimeters, and then schema followed by the schema that is about the 0.6 mm actually. So this how we bring that ions, the singly charged ion from the atmospheric pressure to the at a very low, at a vacuum level, that is about 10 to minus 6 top. And I think I already told you why we need this kind of a low vacuum, because we do not want that these ions should interact with the air particle actually. Otherwise, so they have a maximum mean free path, and this, otherwise they will get they will lose all the information. So then, what is job of this ion optics? The role of the ion focusing system is to transport the maximum number of analyte ion from the interface region to the mass analyzer. So basically, the feeding of these various ions and highly efficiently, we use this ion optics, and then in this, what we are doing it, this ion optic it reject both photons, neutrals, and a matrix component. So that also has been rejected by using the ion optics, and that we termed as a omega lens of axis system, no mass bias induced. And what is the omega lens? Ion extraction lenses in ICP-MS perform an essential function of separating the ions from the photons and residual neutral material for the lowest background signals and the highest sensitivity with the difference interferences, removals. And then we'll see the collision reactions. Actually, what is the utilization of a collision reaction to avoid these various polyatomic interferences. They are the various kind of mass analyzer, that is the quadrupole, magnetic sectors, and the time of flight. See, that's just I told you that collision reaction cell actually. This is just to avoid this polyatomic interference. As I by now you have understood, this separation is based on detection is based on the M/E ratios, and there are certain similar element. For example, argon and oxygen, combination of argon and oxygen having a mass number of 56, and iron is also 56. Similarly, this arsenic can be can be wrongly counted as an argon chloride, can be wrongly detected as arsenic. Similarly, this chloride, that is chlorine oxygen, can be vanadium. So how to remove this interference? We call this polyatomic interferences. This polyatomic interference can be avoided by using these high resolution mass spectrometers. Nowadays, the multi-collectors in the multi-collector, that is ICP-MS, that is multi-collector coupled plasma mass spectrometer also coming. So there also we can use this polyatomic interference. Otherwise, we can be used by using this reaction cell. See, In what is happening in this collision reaction cell, the cell filled with the gases such as hydrogen, helium, ammonia placed before the analyzer, which consists of a multiple and consists of a multipoles. That is a quadrupole, hexapole, and octapole, and usually operate in a RF only mode, that is a radio frequency only mode. So that's how we can avoid this polyatomic interferences. And what are those polyatomic interferences? You can see these isotopes and various matrix with water, all water, acid, water, acids, and sulfuric acid, organic compounds, and organic and again acids. And these are the corresponding interference actually. Okay, see 39 potassium with a 38 argon and a hydrogen, and then if we are having a resolution, that can be how we resolve it. And this particular diagram we have shown that this iron 56 iron and this argon 40 and oxygen. So how we can resolve by using this reaction cells. So here we can distinctly separate both the iron as well as the peak because of the iron and oxygen, combination of the iron and oxygen. These are almost polyatomic interference cannot be avoided in case of the ICP-MS. This is the basically a disadvantage when we are doing the analysis by carrying out the ICP-MS. These are the various detectors, that is Faraday cup collectors or the electron multiplier. And Surgeon Singh, so this is how various all instrumentation which is coming. So they give say Faraday cables, and then different color schemes are being given, and they will prescribe these are the detection limit. But these are the detection limit in very ideal conditions. Okay, so you have to see those ideal conditions. If you are meeting those ideal conditions, definitely you are going to get this detection limit, because whenever we are doing any kind of a procurement. When we are buying any instrumentation, you always ask that person that you have to demonstrate the detection limit which is prescribed or given in their manuals actually. So this you can always tell him. So these are the strength of this technique. It's a wide elemental coverage, and definitely it's having performance wise very low detection limits, that is some nanograms, that is parts per trillion, and it's a very fast analysis time, wide dynamic range, that is minimum to maximum, that is up to 9 order in a single equations. And we'll get the additional information, that isotopic information is possible by using the mass spectrometry only. And spectral simplicity is a key ICP-MS benefit over the other optical inorganic technique, like we are talking about here, this both FAS, GFAS, and ICP-OS. And these are disadvantages, that is prone to mass interference, and they have a very low tolerance in TDS. If TDS is more than even the cross flow nebulizer will not help you. And difficult to analyze a complicated matrix, because when the matrix is very complicated and complex one, then definitely there are certain issues are coming while doing the calibration as well as doing the analysis. And definitely it's need a more maintenance, and since it need a more maintenance, that's why this associated cost also more than compared to the other optical technique like ICP, OS, or FAS or GFS. So these are the various applications can be used for the clinical and pharmaceuticals, zoological samples, forensic, chemical, petrochemicals, food and agricultures. Now coming to the next, see, we had already studied this gas chromatography. Now we have hyphenated this gas chromatography with the mass spectrometry, and mass spectrometry also we have seen in some details, some brief details in my third lectures in the when we are atomic spectroscopy. So gas chromatography with GCMS, we are hyphenated the gas chromatography with the mass spectrometry. And this is a general how we do that, the sample is fed into the gas chromatograph and do the separations. Then whatever the separate things are coming, it will be fed into the mass spectrometers. And then we do we have done the detections actually. So that's how it's shown. The principles, again, the gas chromatography utilize a capillary column and whose property regarding molecule separation depend on the column dimensions as well as the phase properties. The difference in chemical property between different molecules in the mixtures and the relative affinity for the stationary phase of the column will promote separation of the molecule as the sample travels the length of the column. The molecule retained by the column and an elute from the column at different times called the retention that will termed as the retention time. And this allows the mass spectrometers downstream to capture, ionize, accelerate, reflect, detect, and the ionized molecule separately. The mass spectrometer does this by breaking each molecule into ionized fragments and detecting these fragments using the mass to charge ratios. This is how the general schematic of this GCMS. Okay, so this is how this the sample has been introduced into the GC, and once the sample has been come out from the GC, it has been put with the to the ion source, and from the ion source it will be fed into the mass analyzers. From the mass analyzers, the things will come to the detectors, and then we have a control electronics are there. See, this is how we see here that vacuum systems are there. See, once the oils are generated, it has to be before feeding into mass analyzer, they have to maintain that vacuum. This is how this GCMS looks from the outside, and whatever the on the top you have seen this is basically a auto samplers unit is there. And again, this application is vast that is used for the elucidation of the structure of the volatile organic and the biological molecules. Macromolecules mass like peptides, proteins, and oligonucleotides, monitoring gases in patient breath during surgery, identification of drug abuse and metabolites of drug abuse in blood, urine, and saliva, determination of pesticide residues and food, environmental monitoring and cleanup. GCs again is very useful for measuring the various polyaromatic hydrocarbons and pesticides in the environment. And also the analysis of the pesticides done in the various food, beverage, and vegetable samples. In security system, for example, for detection of this explosive, GCMS is very useful. And astrochemistry also use GCMS for analysis of the materials in mass and saturn, and the analysis of the aerosols which we see they received it from this mass and the saturns. Then in combination of with isotopic labeling of metabolite, the GCMS is used for determining the metabolic activity. In criminal forensic, GCMS analyze the particle from a human body in order to help link a criminal to a crime. The various this criminal scene analysis and then we combine with the various samples of the human body, and then they match both of those things. It is also used for the detection of illegal narcotics, supplement drugs to strip dogs, and then forensic toxicology to find a drugs and poisons in the biological specimen of a suspect as well as in the victim. So these are the various advantages associated with the GCMS. So this we see that one of the pesticide analysis in the food materials is generally contain a pesticide in L18, linden, and both endosulfan, alpha and beta forms. So how in a one go we can do the analysis of this? Not only we separate them as well as we can identify them by using these GCMS. This is how these GC spectra, standard GC spectra of endosulfans, alpha and beta, and both aldrin and linden, along with the composed samples. And then we fed with this mass spectra. So this is how with the mass spectra we can completely identify the various fragmentation associated with both aldrin, linden, endosulfane, alpha, and beta. Then similar use of this liquid chromatography associated with the mass spectrometry, that is termed as LCMS. And in this again, this MS systems, both the LCMS is an analytical chemistry technique that combine the physical separation capability of liquid chromatography. That liquid chromatography may be simple liquid or HPLC. That is high pressure liquid chromatography. The analysis of analysis capability of a mass spectrometry. See, again in this, the liquid chromatography separate mixtures with multiple component, and when this component, before feeding this component, they will be ionized and then fed into the mass spectrometry. And mass spectrometry again will do the detection based on their M by E ratios. And these are the various kind of this HPLCs or liquid chromatography. It can be normal phase, reverse phase, size exclusion, or a ion exchange HPLC. So these are the instrumental setup of LCMS. See, most of these hyphenation technique with this GCMS, so most of the time GCMS is available in most of the R&D labs also. But and LCMS also available in most of the R&D lab. But these hyphenation techniques are very useful in the various pharmaceutical industries. Any pharmaceutical industry must have both GCMS, LCMS, and now you will see that ultra LCMS. Ultra LCMS is nothing but I'll show you in the next slide. So this is again, see, after passing the sample, separation of the sample by using the LC, it will fed into the ionize it and then fed into to this mass spectrometer, and that's how we do the detection. So here, this ionization of the sample which is coming out from this liquid chromatography system, it can be ionized by using the can be used by using the electrospray spray interface, or we can use this atmospheric pressure chemical ionization. See what is happening in case of this electrospray interface. The liquid which is coming out from this chromatography forced to a narrow capillary and subjected to a strong electric field. Charged droplet of analyte in solvent are produced, and the solvent is removed by the evaporation. As the solvent is removed, the analyte molecules are forced closer together until they repel and explode. And that is why they repel and why they explode, because of the Coulombic fissions into ions, and then these ions are fed into the mass analyzers. So what is happening in case of these atmospheric pressures? The element from this LC is directly into nebulizer where it is subjected to a high speed flow of a nitrogen gas, and the analyte and solvent droplet pass through a heated quartz tube, so that when the hot gas arrives at the reaction site of the source, it has been chemically ionized by a proton transfer, and the mobile phase acts as a ionization gas, and then how we can generate these ions, and these ions will be fed into the mass analyzers. So this is how in case of a LCMS, we ionize, either we can use the electrospray spray interface, or we may have this atmospheric pressure chemical ionizations. And this is how this three-dimensional spectrum of a LCMS. So this is how this separation has been done by using the liquid chromatography. And then after separation of each peak, what is the mass spectra? That is the various mass associated with those particular elements. This ultra high performance, that is UPLC, MSMS. Okay, this is the liquid chromatography attached with these two mass spectrometers. And here ultra high is nothing but this is basically a patented name given by one of the company termed as a water. Basically they are the famous make of the LCMSMS. That is company name is Water. And in the UCLC, what is the advantage that they have a particle size of it in the range of 1.7 microns, which is the columns are made of 1 micron particles. And based on the event divider equation, it is shown that the smaller particle size increase efficiency without compromising the flow rate for the linear velocity. Ultra performance is associated with increased capacity as well as the improved resolutions of the higher speeds are there. So this is how we can increase the sensitivity of this particular instrument. So this is a use of a triple quarter pole tandem mask. So basically it's a MS designed for the high speed sensitive analysis. And to tune for MS, a collision gas is introduced to the collision cell, varying the collision energy, produce different fragment, and the production of the fragment from a parent ion is referred to as a transition. And at least, the two transitions should be selected for each compound to be analyzed, and tuning for each compound is necessary to ensure a sensitive quantitative analysis. See, again, in this case also, see, whenever even though your hyphenated techniques are there, see, again, you need a standard. Actually. See, without standard, no analysis is possible. So you should have a standard. Basically, this is the standard may not be here as a matrix matching, but at least you have a standard solutions are there, and with the help of those things, one can do the calculation. So this is basically, alpha toxin, study of the alpha toxin. Alpha toxin is nothing but a toxic metabolite produced by a certain fungi in foods. And this figure show the total ion chromatographs of 4 alpha toxins. And each could be uniformly identified when it is LC is combined with the MS. Then each of these alpha toxins is identified their mass spectra. So these are the various peak of 1, 2, 3, 4. That is alpha toxins G2 alpha toxin G1 alpha toxin B2 and alpha toxin B1. So these are their corresponding mass spectra, and that's how we can do the separation as well as the identification of the metabolites. This is the tandem mass spectrometer. See, in the tandem mass spectrometer, also known as MSMS or MS square, is a technique in the instrumental analysis where two or more analyzers are coupled together using an additional reaction step to increase their ability to analyze the chemical samples. And the common use of tandem mass spectrometer is the analysis of biomolecules such as protein and peptides. This is how this the fragmentation, which is first the ionization has been done. In the first step, the ionization is done by either using the electron spray ionization or MALDI or EI, and then it will fed into the first spectrometers, and then from there these fragments will be fed into the second mass spectrometer, and then finally we do the detections. See, the molecules of a given samples are analyzed and the first spectrometer separate these ions by their mass to charge ratios, and the ions of a particular M by Z ratio coming from S1 are selected and then made to split into smaller fragment ions by the following technique. What are those techniques are there? We can use the collagen induced dissociation, ion molecules reactions, or photo dissociation. And these then introduced into the second mass spectrometers, which in turn separate the fragment by again their M by Z ratio and detect them. And the fragmentation step make it possible to identify and separate ions that is smaller M by Z ratio in the regular mass spectrometer. This is how the mass spectrum showing this is because of the first mass spectrometer, and then this particularly selectively when introduced into the second one. See, the mass spectrum has been show the protection of the various daughter ions. And then in this particular example, it has been shown this isobaric labeling using the tandem mass spectrometers. The proteins are extracted from cell, digested, and labeled with tag of a same mass. When fragmentation during the MSMS, the reporter ions show the relative amounts of the peptides. This is how we have done the tagging. Okay, and then mix it. After mixing it, it is fed into the first mass spectrometer, and from the ions from the structure ions from this first mass spectrometer fed into second one, and then to the reported regions. Then this this is about the liquid chromatography, nuclear magnetic resonance spectroscopy. So here we have a hyphenation of this liquid chromatography with the NMR. As you know, that NMR is one of the most powerful technique for the structural isolation of organic compound. And this separation and isolation of the individual component of a mixture, the normal step before analyzing their structure by NMR. So prior to isolations, LCMS is used routinely to analyze the components of the mixture to evaluate the need to isolate the compound of interest. In many cases, however, NMR is necessary for the identification of the ambiguous structures. Even though hyphenated LC-NMR has been shown since the late 1970s, the technique was not implemented widely until the last 2 decades. And for a complete structure analysis, LCMS or LC-NMR have been combined. You know, it's become more versatile by using the combine of the LC, NMR, and MS with this efficiency demonstrated successfully. And that's how we do the various structure elucidation by using the LC, NMR, and MS. See, these are simple principles of the NMRs on what basis the existence of the NMRs, why these NMR signals are appears. The principle behind the NMR is that many nuclei have a spin and all nuclei are electrically charged. And if the external magnetic field is applied, an energy transfer is possible between the base energy to a high energy level. Okay, that's how I'll show you in the next PowerPoint how this, the energy levels look like in case of this particular NMR. The energy transfer takes at a wavelength that corresponds to radio frequency, and when the spin returns to the base level, energy is emitted at the same frequency. That's how the NMR signal is produced. And the signal that matches this transfer is measured in many ways and processed in order to yield an NMR spectrum for the nucleus concerned. This is how, because these nuclei are electrically charged and have a spin, because that's how, clockwise and anti-clockwise, because of that the energy variation is concerned. And when this gap was met by the external magnetic field, that's how we generate the NMR signals actually. This is how this, representation of this diagrammatic representation of the LC NMR. An advantage of this LC, NMR, and MS, the information between the two techniques so orthogonal that HPLC methods resolve complexity of a mixture by separation. NMR resolve virtually any structure quotients, and the NMR can determine if the LC peaks impure. And LC, MS, the ultimate instrument, the NMR data can be taken without complete separation of the mixtures are there. So that's how these are the basic advantages of using this combination of the LC, NMR, and then fed into signal into the MS. These are the precautions and application while using the LC-NMR. So application may, apart from pharmaceutical industry for drug and metabolites, LC-NMR MS is successfully utilized in several other areas such as analysis of natural product extract, that is flora and fauna, and combinational peptide mixtures, food extract, and polymers. There is another technique which is the LCFTIR there. Again, in case of the LCR, whatever the separation has been done by using this liquid chromatography, then the sample has to be evaporated because it has to free from the solvent, and then material has been used for the FTIR. And this solvent removal can be affected by using this cyclone evaporators. So these are these working of the cyclone evaporators. These are the mixtures solution coming out from this LC. Then thermal nebulization take place. It will fed to these cyclone evaporators, and then air cooled condensers are there because of whatever the solvents are there. They will be chill condensed and waste will come here, and then after doing those, it will be taken for the analysis. The solid sample will be taken for the analysis. Then again, these are the certain application of this LC-FTIR. See, as I told you, I think before beginning of this lecture, because this nowadays is not necessary that you will know the concentration of the metal ions or the element of interest. You know in what form it is present with its chemical form, because its toxicity basically depend on that particular forms are there. So that's how these techniques are very important. So these are some of the cases, for example, in arsenic speciations, and these are various way for determination of this arsenic. For example, arsenic is attached with this MMA and DMA, and then it can be done by using the HPLC, ICP-MS, and matrix can maybe have these surface water, maybe water. So these are the various analytes are there. So these are the various analytes are there, and you can see that various speciations of the arsenics are there, and then there are the various analytical column. Actually, we can use for the separate them, and for separate them, we can use these are the mobile phase are there, technique used, and the matrix there. And so, each thing having its own toxicity. Okay. And depending, once you have if you don't have this kind of a hyphenated technique, it is not possible to do. Because if you take the sample, for example, the fish sample, you take it. See, you will not able to detect the arsenic complexion with MA or DMA. Okay, you will just end up with because you will completely digest your sample and all the complex you will break and then finally you will determine all the total arsenic concentrations. So it's very important to use these hyphenated techniques, and the exact speciation determination is possible only when you use these hyphenated techniques. And similarly, in case of the antimony, so these are the various analytes are there, analytical column, mobile phase, the methods of separation, and these are the metrics which started from the plant to the soil and some biological sample like urine and plant extract. So this is how we can do this analysis. With this, we are going to end up the today lectures. But in today lecture, this hyphenated technique, the knowledge of the hyphenated techniques in the today researcher is most essential and a crucial one. Because as the science progress, now we are nobody is interested. For example, Surgeon Singh has the uranium, but nobody is interested in knowing the total uranium, whether uranium is present in which oxidation state, whether the uranium is present as a uranyl ion or whether it's complex with the any uranium. Because the depending on this physical is chemicals nature, the dissolutions of that uranium in the body fluids varies. So that's how very important and crucial to use the uranium speciation. Sajan, I think you are working on the uranium. See, you can talk to me one-to-one because the determination of the uranium, because uranium having many very complex species are there, and then the determination so far, This I have not gone through, I have not done it, but definitely the inorganic speciations may that whether the uranyl ions are there or simple uranium contents are there. And then some of the uranium, I have done the uranium physical speciation. Physical speciation, actually, I have not covered it in my lecture, but it is one of my most trusted, research topic. That physical speciation. See, once physical speciations in the aquatic system. See, all these metal ions, for example, uranium also we talks about mostly on the aquatic system only. So their physical speciation is very important. And this physical speciation means that I told you the water, once you filter the water sample from the 0.45 micron, then there are particles, associated from the 0.45 micron to zero point 0.6 nanometer. And these are the smaller particles from 0.45 micron to 0.6 nanometers. Either they are, belongs to the high molecular weight compound like the humic acid or the fulvic acids. So those things can be done by using the ultrafiltration. So there are the various membrane filters are available, sir. And in the various zone, you can do, for example, 0.45 microns. You can come to 0.22 micron. From 0.22 micron, we go to the some 3 lakh, about say 3 lakhs MNW, that is nominal molecular weight compound or organic compound. So like that, there are the various stages of filters are there. So that I have done it. But as such, the other spatial technique I have not used myself so far. But we can discuss the uranium speciation when we talk in one-to-one, because itself is a very, it's a very time-consuming and lengthy issues are there. Anything else, Sajan? What is your interest in uranium, Sajan? Hello? Sajan, you can unmute yourself. Sajan, Mr. Singh. अच्छा can you write yourself on the chat box, because your voice is not coming here at all. Yeah, I really, because uranium is one of my favorite subject, and we have done a lot of research, not only myself, even in my group also. So we're very happy to share our knowledge with you. But let me know what is your interest of doing the uranium, because we have done a lot of work in Punjab region, as well as we have developed many solvent actually, that we have developed many hybrid material which selectively take out the uranium in the potable waters. And we, because that the detection limit of whatever the prescribed limit by this WHO is about 30 ppb. So that's how we are. Yes, Sajid, we have done a lot of work with the uranium speciation and the uranium milling. I do not know from where you are actually now. You are from DE? Sajid, say, Mr. Singh, you are from DE? Hello? From where? You belongs to what, Jadugoda, Trumbapalli, or where? Uh, agree, I understand that you belongs to HPD, that's what I understood from Jadugoda. Okay. But Jadugoda, see, Jadugoda, I'm associated myself from 1988 onward. Because, my first joining in I belongs to health physics division only, because in 2009 only I transferred from the health physics division to this analytical chemistry. So earlier I have a lot of work on this because Jha and Jha, along with the Jha and Jha, you have done a lot of things actually. You may not be knowing, I think, the retired actually, this work. But due to some reason, I will not speak right now. So we can discuss when we talk about, one-to-one. Because you know that the importance of the uranium in DAE, and so we can discuss this thing one-to-one. You are from, we can discuss it one to one. Okay, with this, thank you all. Now we will see on Monday, 4 o'clock. Yes, sir. Goodbye. Sorry, Bob.